All right, welcome back. We are COMP1115. That's Game Programming 1 in the fall 2025 semester at Georgian, and it's week 13, part 2 of our broadcast and recording. In the previous kind of recording that we made, I did a couple things. I talked about the final exam, and I did a review of our code. I also fixed a bug with you and put it up on GitHub, so you guys could have that information as well. And in this part, what I want to briefly go through is kind of an intro to object-oriented programming, what that is, and so that you've heard this. This is a kind of a semi-formal way of doing it. Again, one thing to note again as we move forward is that this topic is going to be covered in great detail, right, in the second semester, right? So that's what's happening. So object-oriented programming. I mean, you've learned a lot of different things. You've learned variables. You've learned about control structures, if, then, else, switch, case, those kind of things. You've learned about and conditionals, right? How to create conditional statements that kind of trigger the if, then, else. You've also learned about looping. You can loop through, which is a repeated code section that you want to loop through all the time. You've learned about arrays. You've learned about lists. You've learned about enums. You've learned about structs. You've learned about Windows Forms and how you have a platform that you can use some of that code to create user interfaces, all that stuff. But it's not enough. None of those things equate to everything that you need to know to become a great programmer. Without knowing about object-oriented programming, it's like you're missing something. There's a kind of our the knowledge that you have is still far from complete, like it says here. So now there are some opinions about object-oriented programming. Object-oriented programming is not the be-all and end-all, that's for sure. It's just a design, kind of pattern, if you will, or a style of programming. There's also something called functional programming. Functional programming is kind of how we've been going along up until now, right? Mostly, for the most part. We've been using some classes. We're not really doing any inheritance or anything like that, and we haven't really been following any kind of encapsulation. And we'll talk about all those things. Those are the principles of object-oriented programming. Again, all those things and more you're going to learn in the next semester with Wallace. He's going to go through it with you. I know the plan right now is for him to go through it with you in Unity for the most part. We'll see how that goes. And I think it's going to be a good, kind of way of learning more Unity in a more deeper way. And that'll help you with developing your game for Rise, the Rise competition that's coming up in April. So again, really excited about that for you guys. Looking forward to seeing your games. So let's see what the next part is. So what is OOP anyway? So object-oriented programming, like I said, is a style of programming. And what it does is what we want to do is create objects. That's what it is. I want to create an object. And really what an object is it puts together two things, data and behavior, right? That's what we want to put together. So I want to hold some kind of data that I have for that particular object, and I want that object to do something, right? And they could be anything. Objects can be all kinds of stuff. You've seen game objects in Unity. Those are objects, right? So it could be a player, an enemy, a weapon, an item. It could be a platform. It could be whatever, right? And whether it's visual or whether it's not visual, we can create objects, right? That are based off of something called classes, right? So basically what it is a program then is a collection, even a game is a collection of interacting objects. The two commercial game engines that we use right now, which are Unity and Unreal Engine here at Georgian, both use object-oriented programming. And here's the controversy. Do you need it? And I will talk about why some people may say you don't need it, as an example. Or it's really, really fat, and that kind of stuff. And I mean fat, like from a memory perspective. So there might be that discussion as well at some point when we're here at Georgian. But our two commercial game engines, Unity and Unreal Engine, they both use it, right? So you need to learn this kind of stuff. Especially now as you're programming your game, you're going to see more and more. You need to understand what classes do and how they work, right? So when we think about OOP as a concept, let's think about this. If I have a player has maybe health, a name, a weapon, and they have some things that they can do. They can attack, maybe, and take damage. Those are the two things they can do. Maybe there's other things they can do as well. An enemy also has health, and they have an attack behavior. They have movement. They have a bunch of stuff. All these things are example of, I want to model real world objects. The idea of putting together something in my mind from that's in the real world, let's say, and I want to take that real world stuff and kind of duplicate it in code somehow. So OOP helps us do that more than anything else. All right, so that's what it allows us to do. It allows us to it allows us to kind of look at the world and create like I said, look at those business rules or requirements that we see in real world scenarios, and then try and match code to those scenarios. That's what it does. So why do we use it? Because basically what we want to do is we want to code or group code together into these logical units, like we said, right? And you've been seeing that already. Windows Forms is a good example of how code has been grouped together into logical units. Every class, every form is a class. That's what it is. You've been using classes and object-oriented programming, whether you know it or not, whether you like it or not, since the first day you were programming, whether you were programming here with me or whether you open up a Unity project. You've been using OOP the entire time, right? And the other way we can think about it, have you been using OOP or has OOP been using you, right? And sometimes I think it's the latter, right? So one thing that OOP does support which is object-oriented programming again, is it supports these larger programs over time, these monolithic monsters, if you will, of code, where we have multiple classes all over the place, and each class interacts with each other, which we'll talk about as you move forward in your career. So game development, it's super huge from a game development perspective because, again, if we think about some examples, a player object can manage its own health, right? That's what it does. It has a health attribute as an example, and it manages it. An enemy object can update its own artificial intelligence, its own brain, right? It can kind of update and move around and do stuff. A weapon object can calculate its own damage, right? So it knows what kind of damage it can do if it's swung or it hits something else or if it's fired at somebody. A game controller object can track all active objects. We might have game controllers that you've set up in Unity for your levels. It's up to you, right? So a lot of interacting parts, and OOP helps us control all of this complexity as opposed to, having functions, everything functional. Do you want to call this function and that function? And if there's no container, it becomes like one massive monolithic, program, which is very difficult to maintain and troubleshoot, right? So that's the problem with having one big file that does everything. By the way, people program that way. Positive things about functional programming when it comes to game dev is it's super light from a memory perspective. You only have few files. You don't have a lot, kind of thing. You don't have complex structures. The structures are simple. The negative thing about programming that way, it can be very complex, very, very complex, because what happens is you have to know where everything is. OOP has become such a good design pattern that if you go to any place to program, you're probably going to use some form of it or another where you go. People know about it, right? So if you go there and you don't know about OOP and they're like, hey, look, we're inheriting, this object inherits from that one, and that kind of language. And if you don't know what they're talking about, it's to your disadvantage, right? So, but you need to know that there's also other stuff out there that is not object-oriented, that is functional, or other kinds of or procedural, if you will. All right, so that's why it's especially really good. Things that you already know, we talked about already: variables, conditionals, loops, arrays, methods, enums, and structs. These are all the things that classes build upon, right? You need all those things when you're programming OOP, and I've kind of slowly been getting you closer and closer to this day, where you've learned all the fundamentals, and this is yet another fundamental building block of your C Sharp. And whether you do C Sharp or C++ or Java or JavaScript or any other language in the future, a lot of them, most of them, are object-oriented. Okay, so that's what they have. And I mean object-oriented first. Like C Sharp, you can't do a C Sharp program really without having a class wrapped around it, which is what we saw. Same thing with Java. You can do this with C++. You don't need a program like object orientation to work in C++. And C++, as you will learn in second year, is a beast of a language. It allows you to do a lot of things, including break your code very easily. You have to memory manage yourself. A lot of things that you've been getting with C# this semester is a lot of automatic garbage collection and memory management and all the things that we haven't talked about really that happen under the hood that are doing things. There are things that are happening for you as opposed to you doing things manually yourself. All right, so that's something that is going on. When we look at here's two examples. One of them is at the very high level. If I look at a struct and a class, you can see here that they're almost identical, except for the word struct or class. And they can work this way if you want them to. So it's very easy for us to interpose a class instead of a struct. So why would I use a struct if I can use a class? Like, what's the advantage, disadvantage? Well, structs are really great, like we learned last week, for grouping things together, right? If I want to create a little data type and I don't need any behavior, that's where probably I would use structs. Structs are also value types. That means they get passed by value. We talked about that last time when we were talking about methods. So they are copied. So it's great for things like positions and small data. Okay, they're not really for anything else. Classes are reference types. They're more like arrays or lists and that kind of thing than they are like strings or integers. Okay, so that's one thing to know about them. So classes can be, you can create a reference to the class. So you can use ref and out and those kind of things as well with structs if you really want to. But with classes, it's automatic. It's automatically a reference. You make a reference to the class when you pass it in. Right, so that's something to note. And they also use something called the heap. We haven't really talked about memory management too much. You'll get more of that in second year, right? But, and some probably in next semester as well, when Wallace talks to you guys about maybe heap and the stack. So the stack is where we do some stuff when I'm doing things like calculations, when I'm calling methods and those kind of things. I use the stack. It's a different part of our memory, right? The heap is a larger part of our memory where we can use all the other parts. We want to really expand our memory. And classes use the heap, which is a large memory area, like I said. So classes really great for complex objects. Structs are really great for simple little things that you want to do. And that's the difference between one and the other. Okay, so pass by reference automatically as opposed to pass by value. So these are the two things you can see, like they're almost identical except for class and struct, the names. That's all that's happening here so far, right? In this example, they can look the same. In fact, even structs can have methods, but we typically, from a convention, don't do that. All right. I want to pause there before we get into classes. I wanted to talk really briefly about just an intro to OOP, and we're sitting at about 9:08. Maybe we'll continue a little bit more, and then we'll take a short break. I think we're still good. We haven't done a lot, and so we'll continue on with classes. So a class, what is it then? If we've talked about OOP as kind of a higher level concept, a programming design pattern, if you will, right? So what is a class? I like to think about it as a blueprint. Again, it's talked about as a blueprint in many books that you might read about object-oriented programming and so on. What does it do? So remember, we want to create an object from a class. Objects we've seen already. We've made some of those objects already. A form is an object, right? So again, if I go back to some real world examples here, let's take a look at a typical form that we have as an example. We'll look at the program.cs file. What's happening here? Well, remember that forms, when we create them, we have all of these classes here in our project. And for example, the splash form is an object that we're creating, right? Splash form. It is an object of type splash form. Let me explain that again one more time. Here is the class name. So I'm going to just do some annotation here so you're aware of what's happening here. So Here, let's use a different shape because I want to use one of these. So let's say, so splash form then, this part right here is the class. That's the class, right? And then splash form next to it, that's the object, right? So just like we did, you know, with everything else we make, right? When we create a type, right? We have bool, which is the type, right? And we have is exiting is the variable. Same idea, right? So bool is a type. Splash form is a class, but we can also think about the class is also our custom type. It's our type. It's like bool or string or integer or float or whatever, right? That we want to use, right? So that's kind of what these are, right? They're kind of related to those things. And same thing goes with, you know, list, right? List is also a construct. It's a collection. And form is the type of list. Form, we said form, right? As opposed to a specific form. This talks about the superclass, the class that all these other forms come from. And I'm going to try just briefly talk about that. Again, I don't need you to remember, you know, all the nitty gritty details right now because for a couple of reasons. One, again, you're going to learn about this in more detail next semester. I just want you to get a very broad overview right now of some of the things. So if I looked at something like start form, let's just look at that one for a second, right? If I look at start form, and if I look at my class start form, there's a couple things. It says we have this partial keyword, which is unique for this example because we're using Windows forms. But just ignoring this for a second, we have a couple things here. Class keyword, the public keyword, the start form name, that's the name of the class, right? Then we have a colon, which means inherits from, and then we have form. Form is the superclass. So that's what this is. This is kind of like the parent class of these ones. And that's how we do inheritance. Now, again, you're going to learn more about this, but that means every form has an is-a relationship with its parent. So start form is a form. We know that, right? And what it does with inheritance, which we'll learn about next semester, like I said, is everything that's inside form is inherited by start form. And if I was to look at form, if I was actually to look at, like, you know, take a look at what form looks like, and I can do that perhaps by pressing F12, right? Again, if you have ReSharper, it'll do it for you. You can see what it's doing is it's trying to look at, trying to find this stuff. I have to tell you that form is probably massive in terms of what it has in it, okay? So this is the form class. You can see that it also inherits from container control. Yeah, there's actually another class that it inherits from, right? It's a cascade of inheritance, and we'll talk about that again more next semester. You can see that there are a lot of attributes that are created, and you can see that the class form, if I go all the way to the bottom, right, is 6,000 lines long, right? So that's how big the class form is, right? And that means, if in a broad sense, I'm just going to kind of close this off because we don't want to care about this right now. That means that your start form is at least 6,000 lines long. At least 6,000 lines long. Your start form has all that data bundled into it, right? Because we're inheriting. That's the power of OOP. We've made a lot of generic things happen in form, and now we're inheriting in start form. Let me go one more step further than that. So if I go back to form for a second, and if I look at container control, let's see if I can go there and if I can see what container control is. Container control, right, which is another class, right? And if I scroll down, container control also has 2,000 lines of code. So that's another 2,000 lines of code that it has, right? So now we're talking about 8,000 lines of code your code has, for sure, because everything that the other forms have, you have when you're using your form. Okay, scrollable control and I control, this is an interface, but scrollable control is the thing that container control inherits from. Okay, let's look there. Let's go down the rabbit hole here. Scrollable control, so we had 2,000 lines. Scrollable control is another 1,500 lines. So now we're like 9,500 lines of code so far for your form, right? Scrollable control inherits from control. Okay, let's look there. So let's see how that goes down the pipe. So control, can we get there? I don't know if my system will allow me to go that far. Probably won't. Can I go to definition? Let's see. Yeah, it won't allow me to go further because I'm opening up more and more of the underbelly of Windows form. So it's probably another set of like thousands of stuff. Control itself is probably very complex, right? And that's why it doesn't let me go further. I can't go further down to. Let's see if I can peek. Can I peek into it? Yeah, it won't allow me to. Oh, there it is. So control inherits from component. Okay, there it is. And control has, let's see how many lines of code. Oh, you're gonna love this one. 13,000 lines of code. That's control, right? So that's another 13,000. So we're like 9,500. So we're like 25,000 lines of code, let's say, or 22,000 lines of code so far. All right, that's control. And control inherits from component. Okay, well let's peek at that one too. Peek definition. Well, component, right, has another 100 lines of code, right? And component inherits from Marshall by ref object. I don't think we can go further than this, but let's peek at that one too. It's another couple hundred lines of code. This one's another couple hundred lines or 50 lines of code, and that doesn't inherit from everything. So this is the true abstract superclass of everything. The Marshall by ref object. Crazy. That's what I think it is. It's crazy. So we're looking at, before it even gets to you, this is why I wanted to show you this. Before, a form even becomes start form, we have baggage of about 20 something thousand lines, 23,000, let's say 24,000 lines of code. So why am I telling you this? Because if I go back to the problems with OOP, what is a class? A class is a blueprint, right? And we can have classes above this class that are blueprints for other classes, and we're going to talk about that again in great detail next semester. But I want you to, when you go down that rabbit hole, you might, kind of learn things like this. Classes can be fat from a memory perspective. It takes all those lines of code have to be consumed. It's all carried in memory. Whenever I create an object, I create an object with all that stuff, right? So, they're useful. They're very useful, but they have a lot of stuff that's in them, and it's clear that they would, right? Because if you were to look at something like a Windows form, like actually the designer part, which is another set of controls and things that you need, right? You have all these properties. Look at all this stuff. This is all the stuff that's included in a class, right? All these properties that are there that you can modify. You can change, kind of the value of all the properties that are here. So it must be big. It must be big. It must be something like this large, right? And they're so, you can put them together like building blocks to create your Windows form. So, this is where the complexity comes into play. But going back to this then, if that's what classes are, if classes are blueprints to create other objects, where we have, like we said before, the object for us is called start form. The class is called start form. We just happen to call our form in program.cs. We called it start form. That's what we called it, right? That's the name of the class. This is the name of the variable. This is the name. It's the same name. You can do that, right? It's not recommended 100% to do this all the time, but this is allowed, right? As an example. So first we declare, kind of the class itself. And then one thing that we need to do is use the new keyword. The new keyword breathes life into the class. It kind of basically creates the object. That's what it does. So that object now is alive at runtime, and we can use it just like we've done with our Windows form, right? So that's what it does. So that is what a class is. It's a blueprint. And a class, let's talk about the anatomy of a class a little bit. Like what are the components of a class? Well, we have fields. Usually fields are private, okay? So we'll talk about those little modifiers here. But fields, I want you to think about them as member variables. Sometimes they're also called instance members. There's many names for the same things in OOP. And usually what we want to think about them is they're variables that hold internal data that cannot escape without going through some kind of door. And the door is going to be the property, right? The property is going to be your gatekeeper, if you will. It's going to be the entry point. Where you want to get data, you got to go through the property. That's the way classes usually try and go and make things happen. right? So if I want to get through the health lowercase h property, I got to go through the health uppercase h. So I want to go to the health field. I want to go through the health property. So properties are controlled access to fields, like we're going to talk about later on. And then methods, that's another one, another construct. Methods are actions. We've seen what methods can do. You can pass parameters to methods. They can return things. Lots and lots of things that we learned about when it came to methods. That's also a thing. There's a method. And we have a special type of method called constructors. We've also talked about this. And the constructor is something that triggers the first time, or they run once, when you create an object. So whenever I create a new object, the constructor kind of is created. One thing to know about the constructor method, it has the same name as the class. So if the class is called player, then the constructor is also called player. All right, that's kind of the thing that you'll see. Unity does this the same way as well. Okay, except in Unity you have two methods, start and update. And start, you don't see the constructor function for Unity, but it's actually there. If you wanted to, do something in the constructor function, you could, right? It's not recommended because Unity uses C# as a scripting language, right? So it's just be aware of that. But the constructor function has a special role, and a lot of times what it does is initialization. So if we declare a field up here, we have an entry point, a way of getting data to and from the field here with get and set. The get and set allows us to get data from the field and assign data to the field. So this is, again, like our door, our entry point into the field data itself, right? And then the constructor function gets called, and we want to initialize the field with some kind of default data, right? As an example, maybe 100 by default. Maybe health is always 100 by default in this case for players, right? We also have a method, and this method is the amount of damage that the health will take. So you can see that damage amount comes in as a parameter, and then we subtract it from health. So health minus equals, remember, is a shortcut for health is equal to health minus amount. That's what it means. That's what minus equal means, right? So that is an example of the anatomy of a class, right? When we create a class, again, if we think about this, right, we have two things, right? We want to have fields, right, is the first thing we want to do. We want to build them with fields. And then our field declarations have something called the private access modifier. We're going to talk more about modifiers. There are three different types of modifiers: private, protected, and public. Actually, let's look at them the other way around: public, protected, and private. And each one of these in order are more restrictive. So if I go public, it's the least restrictive. That means anyone can access data from that field or from that property. If I go protected, only data members that are from this class, the class that I have, and its child classes can access those fields, right? Again, that's something you're going to learn about next semester. And then private means only the class can access those fields. Anything outside of that class, it's not even available through the dot operator. You can't access those things. It's shut down. And a lot of times we shut down things with private because we don't want direct access to something. We don't want direct access to a method or a field, a variable. That's part of the class. So again, to provide access to our private fields, we use public properties. That's the way we do it. And that's the concept. That's one of the concepts of OOP. Sorry, I'm gonna take a break soon. So again, one thing a lot of times when we make these fields, sometimes they're also called backing fields, is we might have special names for fields. We haven't seen this so far in our code, but M underscore is a way of, you might see that as a coding style, or just underscore. There's two ways you might see it: M underscore or just underscore. Underscore, in your mind, whenever you see a variable that has underscore from now on, with me, with Connor, you're going to meet Connor in year 2, I believe. With anybody that you see, underscore a lot of times means private when you see the underscore character. Right? It's a quick way of knowing that that field is private. M is optional. Depending on what language you're coding in, you might see M, you might not see M. M means member variable. It's part of the class. So a member variable that's private, or a private member variable is what that means. Okay, if you ever see it, it's just a coding style thing. It could also not even have that at all. It really depends on the coding house, the people you're working with. They may decide that they don't want to use that, right? But that is definitely a convention that I've seen in many places, right? So here's your field, and then you have your properties. Your properties look like this, right? So properties are wrap fields and control how values are read and written to. So for example, we have get and set, get and set. Those get and set, notice it has return the name. So I take the name and I return it when I try and get value out of name. You don't need to use get. This is internal. This is something that you would write inside of your class. Outside of the class, if someone who would use the class would only use name, capital N, right? Or health, capital H. They would never see these things. These things would be inaccessible because private. They're private. These are public, right? So that's how they would be seen. There's also one other way to do this. Instead of doing it with a backing field being one of these, right? Then what you can also see is something that looks like this. It's an auto-implemented short form property that you can make without the need of fields at all. C# knows that if all you're doing is this, if you're just like reading and writing data, then it's kind of useless, because really what these are little methods, right? That's what they are. They're almost like a short form way of writing a method. In the curly braces, you can write a whole pile of extra stuff. A good example of this is if I was setting score. If I set the score, so I'm using the set component of the score, then inside the score, before I set the value for the score, when I set it up, if that's what I'm going to do, let's suppose, I can also update my user interface. So I set the value from the score, I update my user interface, and that can be all inside the curly braces. I can't do that if I access these things directly. If I'm accessing data directly, you can't. How are you going to do two things at once? You can't. But if a method can do a bunch of stuff, right? And that's what properties are. Properties not only are the gatekeepers, but properties allow us to do a lot of different things when we're reading from or writing to fields, which is really important. Okay. So that's something. Methods, like we've learned about before, right? Defined actions, right? And here is an example of two methods that are very common in C++ and in Unreal Engine, if you're going to see them. Now, I've written them here in C# just to see how they look, but basically there's take damage and apply damage. So imagine I can do two things. I can take damage as an amount, and I can also apply damage to a particular enemy, right? Where the enemy itself is going to take damage. They also have their own take damage method, okay, as an example. So this is a good example of that. So important notes for this one are methods really describe behavior, like something that you're going to do, right, with your game object or whatever. And then classes, what we want to try and do is we want to try and kind of add methods that make sense. What we don't want is God methods. I'm sorry to say it that way, but these ideas that like methods do everything. This method can load, it can save, it has a lot of different functionality. Once you go down there, it's like, can't you break that method down, that function, into smaller bits? You can a lot of times. And I want you to take that away as well from our discussion today, which is I want you to think about the ability for us to break our code down into smaller pieces, easier for us to digest, to understand, and easier for us to code as well and test. Okay, so that's something that methods allow us to do. Methods are really about behavior. We talked briefly about constructors, and really there's two types that I've ever seen, right? Maybe three, and we'll talk about the third one today as well. A constructor is just a special method that has the same name as the class, right? So again, if I was to go back to our example, we have the class name program, but you notice that we don't have the program method, because this is a special type of class. We're not talking about it this semester, but it's a static class. A static class, very briefly, does not have to be instantiated. It's like a blueprint, but we can put a bunch of stuff in there, and it'll be available whether you instantiate it or not. It's kind of a way of doing functional programming with OOP in many ways, right? That's what the static keyword means. I don't have to instantiate the class to actually have access to any method or property that's marked as static. Okay. Again, I want you to look at it that way for now. And next semester, you'll learn more about what that static word means and what it can help you with. But let's take a look at something else we've had, like a start form. So start form, that's the name of the class. And then, what we can also have is the name of the method that's also start form. Now we don't have, we don't have more than one constructor. All we have is one constructor. This is the constructor. Look, here's the name of the class. Here's a function that has the same name as the class. This must be the constructor. And when you have no parameters for the constructor, it's called the default constructor or the empty constructor, which is what we're showing you here. Empty or default constructor, no parameters. Same name as the class. If the class was called player, this would be the constructor. There's also something called a parameterized constructor, where the constructor does have parameters, right? Both of these two things can live together. You can have both a default constructor and a parameterized constructor in the same class. What this does is it gives you two options for you to create your class. And that's what we say there's two overloads. These are, just like we've said before, they're overloaded methods, but they're special overloaded methods. We've learned about overloaded methods. Overloaded means same name, different parameter list. That's what it really means, right? So that's what's happening here. Same name, different parameter list. Here, no parameters. Here, two parameters. Okay. And then finally, we want to construct objects, right? So let's suppose I have a player. His name, we want to mark it as Conan. And then I want to make a new player. So here's my new keyword. Here's the player. I have to use the class name. And this basically is using the constructor. So here, new player, where I have Conan and 200, I'm going to use the parameterized constructor because this constructor takes a name and health. Here, I'm using a name and health. I'm not using this constructor. I'm using this constructor. And at runtime, your program will know which constructor you're using based on the parameters that you're passing into the code, right? If you pass parameters in the wrong order, or if you don't pass enough parameters, and none of these two match, you'll get an error. It won't allow you to do it. So here we have an enemy, and let's suppose the enemy is very similar in structure to the player. Then here we have another enemy, and then what we can do is we can say Conan apply damage, because the apply damage function, which we talked about it here, takes an amount and an enemy target, right? Then what we can do is when we say apply damage, damage is 20 that goes to Thulsa, that object. Let's suppose Thulsa also has a take damage. It's even though the player has it, maybe the enemy also has the same thing. It goes in here and it takes that 20 damage and it's subtracted from their health amount. That's how it works. And what we do with it is we use the dot operator, or also called the dot accessor, right? To have access to, or whether we want to read, write, or execute, kind of like properties or methods inside the object. So if we have in the class, if we blueprinted out a method called apply damage, we can get access to that through the dot. The dot, we can use the dot operator to have access to it, as long as, and here's the main thing, as long as this apply damage method is public. If it's private, you won't be able to do it. It won't even show up when you press the dot, right? So those are the rules for the most part of instantiation. So again, one thing we can do is we can store objects in arrays or lists. We can also pass objects to functions. So a good example is if we wanted to make an array of enemies, we can simply do something like this. Here's our new class, enemy array, and we've seen this expression that we've done before, which is a collection expression, right? And basically what it is we can use the new keyword without a variable to create, instances. That's what they are, instances of the same of the same class. So different objects. These are different objects. Goblin, orc, troll, vampire, and dragon, are 5 different objects using the same class as a blueprint. Okay, that's what they do. And we can also do the same thing with lists. We can, let's say, a list of type enemy. We'll call that enemies, just like we did array. And we'll say that's a new list of enemy. A lot of times you see this structure where we often create an empty list of type enemy first, and then we add stuff to the list, right? I know, right? I'm just giving you some examples here that are not sci-fi-esque. So we're just using some some other kinds of things for maybe a fantasy game. I like fantasy too. Played D&D for years. So so we can loop over arrays and lists of objects with the same structures we've done before. We can use for loops, while loops, for each loops. We can all the same constructs we can use to loop over kind of objects of there are custom objects that we create. Okay, which is pretty cool. Lots of control. I'm just going to go into some principles and then we're going to take a break, okay? And these principles, I don't need you to 100% remember, but I want you just to understand, just to hear them so you've heard them before. And then maybe when you get into this next semester, you'll know more about them. So these are the four principles that of OOP. And if you go against any one of these principles, we can say that you are violating them. Sorry to say it that way. So the first principle of OOP is encapsulation, which means we want to protect internal data. And what we want to do is we want to have private instance members and public properties. That's the way we're going to do it. We want to validate the data that goes into our forms. We talked about validation earlier this semester, which is that if it wasn't only for that pesky user, then everything would be perfect, right? Well, because the user is going to always try and do things that you don't expect, right? So encapsulation allows us to do some validation right when we read or when we write to our data members. And that's why it's important. Inheritance is what we talked about before. We can create an is-a relationship. For example, here we have an enemy, but we can have a specialized version of that enemy, the zombie enemy, or the vampire enemy, or the star marine might be a special version of a player, right? Where it has specialized information, things that it does differently than, for example, just a standard enemy. In fact, enemy is not really a great descriptor of what it could do. You want more specific reasons why that enemy is. Enemy is just too broad. It's not like you look at someone and say, well, that's it's a person. A person is very abstract. A person can be many things, right? So when we say student, now that's a little bit more specific. And more specific than that would be domestic student, a person that lives, kind of in Canada or from Canada, let's say, as an example. That's more specific as opposed to, or a professor, example. Yeah, so you can see that person is way too broad. It doesn't really tell you much. But then as we get closer and more specialized, then it becomes more understandable. So zombie enemy is probably better class than enemy. Enemy is very high level. Maybe all enemies inherit from the enemy superclass, but for now, that's enough. Polymorphism is a way of changing stuff. So for example, I might have in my superclass an attack function. The attack function is something I might define for all enemies and players, right? Every enemy and player can attack, but every enemy might have different things. Maybe a zombie bites or a robot fires an eye blaster, right? A dragon breathes fire, as an example. They do different things when they attack, and that's polymorphism. Polymorphism comes from the Greek word polymorphy. Sorry to say that, or polymorphes, which means multiple forms, or many forms is what it comes to. Abstraction, right? A lot of times, things are so complex. Here's an abstraction. You've been using a form and you had no idea that there was like 20,000 lines of data, before you used your form. That's abstraction. It's a black box. You're using a, kind of a class, and you have no idea as a user of that class all the lines and all the details underlying everything. You don't need to know all those things. All you need to know is the things you need to do for your application to solve your problem. That's abstraction. So those are the four principles of of OOP, and you're going to learn more about them next semester. Okay. One thing to also note is when we get more and more into OOP, and this is really high level stuff, but I want to talk about it with you so you've heard about it, is there's something called solid design principles. And I don't need you to remember much about this at all either. I want to talk about it with you. When we start programming, we've been really talking about low level stuff, like just really knowing how to create like a variable, or we want to use some kind of control structure, or we want to use a method or whatever, right? That's really like building block stuff. That's really like scratching the surface toy stuff. But once we start building bigger applications and games and stuff like that, you're going to realize that you need to keep things organized. And solid design principles allow us to do that. One thing it says is that every class or method should only do one thing, right? If it does more than one thing, or if it represents more than one thing, maybe you need to break that thing up into smaller pieces. Okay. There's other things that we talk about here as well. Like, for example, open close principle is software should be open for extension, but closed for modification. Um, and there's also the list-off substitution principle, which is subclasses should be usable anywhere the base class is expected. So if I use a zombie, a zombie enemy, it's an enemy, right? Um, and otherwise, it doesn't work properly. If somehow you've made it so that zombie enemies don't do the same things as enemies do, something is wrong. That's not a great design print. Not really a great way to design stuff. Interface segregation is, don't use a lot of dependency. Try and remove dependency from your structures, right? Because again, we have all these high level classes that the low level classes inherit from. There's something else called composition that you're going to learn about in the second semester, which allows us to be more flexible when coding. So this is kind of our solid design principles. You might hear about solid design principles as well. And the last thing, and this is for your own enrichment, if you will, your own reading if you want to, is the Gang of Four. And there are 23 design patterns. So back in 1994, earlier than many of you were alive, these four computer scientists, Eric Gamma, Richard Helm, Ralph Johnson, and John Vlasides, they came up with this idea of design patterns, this book that they wrote. And what they did here is they talked about 23 design patterns that were broken out into these three families: creational, structural, and behavioral. And what they were is, we noticed as we started using OOP, even back then, that there was these repeating patterns, and we wanted to solve problems. And the problems were solved. This is like, for example, a solved problem, like tic-tac-toe. Tic-tac-toe is a solved problem, right? You understand it's a closed loop. It's not an infinite game like chess. Chess has thousands, even though it's a solved problem, there's thousands upon thousands of different ways of playing chess and everything else. But what this does, these provide patterns for us to solve problems with common constructs, where we kind of put things together, as an example that we do all the time. And a good example of that is the observer pattern. The observer pattern, again, which is really a behavioral pattern, if you think about it, is us watching something that changes and then responding to that change. And we do that right now with buttons, right? If I click on a button, I'm a watcher. I'm observing that button, and then what happens is I subscribe to the change. I'm listening for something to happen to that button, and when the button is clicked or the mouse hovers over the button, then I want to respond. The subscriber, which is me, gets notified that the button has been hovered over or clicked, and then I have a chance to respond. Observer pattern. All right, so they've kind of wrapped these names around these things. And again, there's some great things. One thing I want you to know is it's not just about generic stuff, about non-game related stuff. I've given you a link. This is a really great link, and I want you to take a look at it. It's an online book that you can read if you're interested in reading about design patterns early. And it's written by Robert Nystrom. And what he talks about is all the different design patterns that apply to games. And he discusses all this from a C++ perspective in great detail. I think it's been a great book for me when I was, learning about design patterns as well. After I saw this book, I was like, wow, okay, that makes sense now for, game related stuff. So they talk all about this. So if you have a chance to read this over the break, this is a great thing to read. Again, you don't need this for the exam, and even classes will probably not be on your exam because we're just talking about it today at a very high level. But I just wanted you to think about this, because this is kind of an intro into the, into a larger world of programming that that you need to know about at some point. Okay, so that's that. And that's where I want to stop for now. I want to take a short break and come back and actually do some work for your in-class exercise 12. Okay, so let's do that. Questions before we stop? Anybody? Anybody interested in this kind of stuff? As a computer scientist, for me, and that's why I see myself as well, is I'm interested in this kind of stuff. I'm always interested in seeing, these, kind of going to the next horizon of design pattern and taking a look at things that we can do more efficiently and better than we've been doing in the past, right? There's a lot of interesting things to learn. Programming is such a large field. and we're doing kind of a very specific type of programming, game programming. But the stuff that I've been showing you this semester is the stuff that you can transfer from a skills perspective to other professions, not just being a game developer, but also, I don't know, working at a bank or doing something else. All these same structures are useful in other scenarios. You want to build a mobile app, the kind of very, very similar things that we've talked about already. You'll see the same structures there. All right, let's take a short break then. It's 9:44. We'll come back in about 5 minutes. We're going to grab a coffee and we'll continue and finish with our in-class exercise for today.